Hi, I'm Ben-Yaakov. This presentation is entitled Examination of the Inner Works of a Transformer by Simulation. Let me say a few words about the background. A transformer is really a basic device that is used in many electrical, electronics, and power electronic systems. It uses for different tasks like power transfer and sensing. It would seem, however, that since we take it for granted, some might have lost the understanding of how exactly does the transformer transfer voltage, power, and in particular, current. Now this presentation dives into the inner working of the basic transformer using simulation to demonstrate the waveforms and the interrelationship between the signals. So here is how a typical textbook explanation of how a transformer works. Here we have a core. We have, in this particular case, two windings, and when we connect a signal or excitation to, say, V1, it will cause a magnetic flux to build up, and this flux is now coupled to the secondary, assuming that all of it or most of it is enclosed in the ferrite or in the core. So the two fluxes are the same, and then the voltage, according to the Faraday law, is the number of turns times the derivative of the flux. Derivative is the same, and we are getting that V1 over V2 is N1 over N2. Now, usually the explanation invokes the conservation of energy, saying that the power coming in is the power coming out, ignoring losses, and if you do this, you get this ratio of the current is N2 over N1. So this is a very typical explanation. But this does not explain how really this ratio I1 to I2 is equal to N2 over N1. Now obviously the transformer is not measuring power, it's not equating power, so how come that for the voltage we understand very well what is happening, we have a common flux here, but what about the current? Now there are some questions here. For example, if we have an open circuit here and then we connect a load. Now before connecting the load, the flux is given and it is dictated by the voltage. Now we close now the switch, we are loading the secondary, current is building up, current is then reflected to the input, but the flux does not change. So how is this relationship happening? What is really initiating this relationship between the two windings? Another question that could be asked is the following. Now, according to Faraday, we know that the flux is 1 over n, the integral of the voltage. So this is the flux. But according to Ampere's law, the flux is of course related to the current, because the flux is the mu area times the magnetic field. Magnetic field is a function of the current, so therefore the magnetic flux is a function of the current. So which is it? Is the flux a function of the input voltage, or is the flux a function of the current? So it seems to be confusing here. So in order to probe into these issues, I'm setting up now a reluctance model of the magnetic circuit, and this is done by actually expressing the flux as a function of the current, or n times the current, which is the MMF as we call it, and then we have here this term here, which we define 1 over this term, we define it as the reluctance. So reworking this equation, we can express this Ni or MMF as a function of the reluctance times the flux. Now we can emulate this magnetic relationship by an electrical circuit by defining the MMF as voltage, electrical voltage, the reluctance as resistance, and the flux as a current. And by that we can get an equivalent circuit in which the MMF is a voltage source, the reluctance is a resistor, and the flux is the current now passing through this branch. So I'm showing here a ferromagnetic piece, say ferrite, which has a certain length, magnetic length, certain cross-section area, certain number of turns, and this then can be emulated by this electrical circuit. Now we miss an interface between this magnetic circuit and the electrical part, that is these two terminals, and we can do this by having a dependent source, a dependent voltage source defined as NdPdt, which would generate a voltage here depending on the flux that we have in this branch, actually the derivative of the flux. Now we can connect to this dependent source either a excitation, like a voltage source or a current source, or we can load it by a resistor, and then this dependent voltage source will of course feed this resistor if we have a input voltage to the primary. So the relationship between the magnetic and the electrical circuit, the equivalent or the emulating equivalent circuit, is that MMF is voltage, reluctance is resistance, and flux is current. Just to get a better feeling, let's get some numbers. Let's assume that this piece here has the length of 5 centimeter, an area of 1 centimeter square, and then the mu r, the relative permeability of the material, is 5,000. Ferrite would have a relative permeability of say 1,000 to even 10,000, and some other material could go even higher, to even to 100,000, like amorphous materials. And I'm just taking it as an example the 5K number, and then mu sub 0, which is the permeability of air or vacuum, is 1.25 10 to minus 6. So plugging in the numbers, I'll just get the feeling that in this particular case the reluctance is 80K and the units are 1 over Henry. So this is in fact like the A sub L inductance per turn. So by multiplying it by n squared, you get the total inductance of the piece here. And the units, therefore, are 1 over Henry because n does not have any dimension to it. So using this technique, we can describe the transformer with 2 windings by this reluctance equivalent circuit. Here we have the excitation coming from here. We have the back EMF or induced EMF as a voltage source depending on the phi dt within the reluctance path here. And then we have a voltage source which represents the MMF, N times I. And this will be the secondary side, and it is the same. We have here the induced EMF and then the back MMF. So this actually represents this circuit here. And then we can do some simulation, of course, and calculation with this circuit. So let's start off with the basic configuration in which we have only 1 turn. There's no secondary, okay? So this is practically an inductor, okay? It's 1 turn, and here I'm showing an excitation by a voltage source. So this will be the reluctance. We don't have the secondary. And this will be an LT-spice realization of this circuit. I have here dependent voltage sources. This will be for the MMF, and this will be for the back EMF. And here I have a 0 voltage sources, and these are used just for referencing a current. This is the old SPICE method of using a voltage source of 0 voltage as a reference. So when you like to refer to the current here, you refer it as the current of this particular voltage. So this is just a 1-to-1 translation of this reluctance circuit. So let's try to understand what is going on when we have a voltage source here feeding this inductor. We have the voltage source, and this will build a flux within the core according to Faraday's law. And then this flux will actually invoke an MMF source according to this relationship, which is based on the Ampere law, which will then come to a steady state between the voltage, the flux, the MMF, and the current at the input. So we can describe this process as starting with the voltage, generating a flux. This flux is then generating this MMF. The MMF is now causing current at the input. So this will be the process of building up the flux within the core. But it has nothing to do with the transformer as yet. It is important to realize, however, that between the voltage and the flux, there is a 90-degree shift. The reason is that if the voltage, say, is sinusoidal, and the flux is the integral of this voltage, so it'll be like cosine, so the 90-degree shift. So this flux is shifted, actually it's lagging after the voltage, and therefore the current is also lagging after the voltage. Okay, so the MMF and the current then at the input is lagging after the voltage. This means that we have here only reactive power. We have a voltage and then we have a current which is 90-degree shifted, so they are actually orthogonal, you might say, and there is no real power involved in here. So in this situation, we have only reactive power. There is no real power moving from the input anywhere, and what is circulating here is just the reactive power, and that is because the current and the voltage will be 90 degrees shifted, and of course the real power is zero. I can express V as a function of the dt, and here I'm getting the term here. It is recognized as the equation of an inductor. So the value of this inductor is n squared 1 over the reluctance. Reluctance is for one of the pieces. We have 4 pieces here, and for this particular case and the numbers we've used before, I'm getting that the inductance seen here is 31 millihenry. And here are the results of a simulation run of this circuit. What we see here is as expected. We see the input voltage, we see the current lagging, we see the MMF in line with the current, and we see the flux in line with the current. Okay, so the flux is shifted from the input 90 degree because it is related to the Faraday equation, which says that the voltage is related to the derivative of the flux, and if it is a sinusoidal waveform, then you have this phase shift. Now for the current, we find from the simulation that for this particular case, the peak to peak is 1 milliamp, and therefore the peak value is 0.5 milliamp. For the flux, we find that the peak to peak value of the flux here is about 320 nanoweber. Okay, this is from this simulation. Now we see here that the flux has some offset. Okay, it's not around zero. This is a simulation problem because as you start a simulation from zero, you pick up some average value which sort of is locked in, and it's very difficult to get rid of unless you start with very precise initial condition. So I'm skipping this, and we just realized that this is an artifact of the simulation, this DC offset of the flux. Now that we have some numbers from the simulation, we can do some sanity checks. First thing, let's calculate the flux, what is the expected value of the flux, and I'm calculating it from actually Faraday's law, which comes to be V in over 2 pi f n, and this is 160 nanoweber for the peak, and then for the peak to peak is 320 nanoweber, exactly what we found here in the simulation. And for the current, this is the impedance of the inductance, V over I, and it is calculated to be 31 millihenry, and this is what we have calculated before. So there is clearly a very good agreement between the simulation and the expected values. So let's move now to the transformer itself. So what we found up to now is like the lower level. This is the reactive part, has nothing to do with power transfer. It has to do with the magnetization, and now we are adding this power transfer by having another winding, which is in this case loaded by a resistor. So this is again the reluctance equivalent circuit, and this will be the LT-SPICE realization, very similar to what we've seen before. We have the reluctances, we have the dependent sources, everything like before, except that we have now the secondary. And I'm assuming that it is loaded by 10 ohm, and the excitation is 10 volt, so the current should be 1 amp here and 1 amp here. Of course, I'm ignoring losses. This is just a small resistance here. So let's try to track what is really happening when we have a transformer and then we connect to it the load. At the beginning there is no current. Once we connect the load, the current has to build up. So the voltage itself is generating the flux. Okay? This is what we have seen before. This is the reactive part. Now we are starting to have a current because there is a voltage here and we have a resistor, so there is a current here. So this will be the second stage. The third one would be that this current now invokes a MMF, which is causing a change in the flux, which is transferred to the secondary through the core, and this change of flux is causing a current to build up according to Lenz's law. Now this process is just a transient. This delta is disappearing or is non-existing. This is just conceptually, I'm trying to explain the buildup of the current by some imaginary steps. That is, we have a current causing an MMF, causing a change in flux, and then causing a change in current. Eventually, this will stabilize and all these deltas will disappear. And so it will be a stable system in which we have a current here, and therefore we have an MMF here, which is opposing the MMF here. And this MMF means a current at the output, which is causing the MMF on the other hand. So it's like a stable system that causes this relationship to hold. So here are results of simulation of two cases. One is the one that we talked about earlier, and that is with open secondary. So open secondary, there's no real current passing, no real power. And the second case is the one that we are not talking about, and that is with a load of 10 ohm. So let's go back to the open circuit case. In this case, we have a shift between the current and the voltage at the input, and then we have an MMF at the input, and at the output, the MMF is 0. Okay, we have only an MMF at the input. And this MMF is coincide in phase with the flux, which is shifted from the voltage. It coincides with the current. So the current, flux, MMF are in phase, while the voltage is out of phase. Okay? Now we move to the case of 10 ohm load. Here the current and the voltage are in phase. Now we don't see actually the reactive part, because the reactive part is very small. Remember, we were talking about 1 milliamp current peak to peak. Here we're talking about 2 amp peak to peak. So therefore we don't see it. What we see here is only the real part, only the part that is transferring the power. And for this part, the current and the voltage are in phase, while the MMF, which is related to the current, is now shifted from the voltage. Okay? So here's the big difference. Background situation of the reactive operation. We have no shift between the MMF and the flux, while here we have a shift between the MMF and the flux, meaning that these are orthogonal, and the MMF is not the source of the flux. They are not related. They are sort of two separate processes which do not interact one with the other. To understand it better, I'm looking now at the difference between the MMFs. Okay? So in the case of the open circuit, MMF on the input side is this value here, while on the output side it's 0 because there is no current. So the difference between them is just the input side. Now, for the case of a 10 ohm, the difference is the same because this is the difference which is related to the flux, while the major MMF at the input and output, which are the same phase, they are opposing each other, are shifted. So the main MMF is related to the input current, while the reactive power is related to the difference in the MMF, which is very small. And this is what we have seen before. So this is the driving force for the flux, in fact, while these two MMFs of the input and output are equal and of course oppose each other, except that there is a small difference, which is this one, which we don't see because it is small as compared to the MMF itself. So the MMF, due to the input current, is in fact it's 100 ampere turns because it is 1 amp and 100 turns. The difference between the MMF at the input and at the output, which is driving the flux, is only 110 millivolts as before. This does not change with the load. So we see a major MMF, a large peak here because of the input current, but the flux in the core is related to the difference in this MMF, which is reactive. Now this means that the MMF at the input is larger than the MMF at the output. Well, by a small value. This is this value here, okay? It's always, both for the open and for the loaded case, it's the same difference because it has to do with the magnetization. So how come we have two MMFs which are not equal? Well, and the reason is that this difference is actually driving the flux which is passing through the reluctance. So the difference is the drop across the reluctance. So this drop across the reluctance is the difference in the MMF between the input and the output. So to say that in a transformer the MMF are exactly the same is actually neglecting the reactive part, which needs a difference in the MMF between the input and output to maintain the flux within the core. Now the implication of this is that the input current is in fact larger than the output current because they are not the same, the MMF are not the same. And this is explained by the fact that you need a current here to maintain the magnetization, and we usually show it as an LM, a magnetization inductance that needs some current, and therefore it is sort of stealing some of the input current, and the output current is therefore somewhat lower than the input current. So this is the electrical end result of what we have seen in the magnetic circuit. Now if I load the output with an inductor, and this inductor is much smaller, it's 10 microhenry, much smaller than the magnetization inductance, which is about 3,000-fold larger than the load here. So we'll see primarily the current through this 10 microhenry. So now if I look at all the cases we talked about, the open case that is just the inductor by itself, the loaded case with 10 ohm, and then the case with 10 microhenry load, okay? Now these two, this open one and these, should be the same because it's the same phenomena. We are just talking about the reactive power, and you can see very nicely that the MMF and flux are coincide. There's no phase difference between them. On the other hand, with the 10 ohm, we see a shift between the MMF and the flux, and the reason is that we see the MMF due to the real power, and this MMF is orthogonal to the flux, which is related to the voltage and not to the current. Now in the case of a 10 ohm load, we see that there is a shift between the MMF and the flux, and this is because the MMF is now due to the real power, the major part of the MMF is due to the real power, which is, of course, 90 degrees shifted from the flux, which is related to the reactive MMF. And finally, I'm showing here what happens if we have some DC. Now, DC obviously is not transferred through the transformer because you need a change in flux in order to move power from one side to another. So it is just affecting the winding that sees this DC. And in this particular case, I have connected it to the output. And what it's causing is a shift in the flux. You see that originally, without the DC, we are talking about 330 nanoweber, while here it's already 2.8 microweber due to the shift caused by this 100 millivolt DC. Obviously, if the shift is too large, and if we're talking about a ferromagnetic material, a physical ferromagnetic material, then we have a problem of saturation, which is of course not dealt with in this presentation. So what are the conclusions of this presentation? First of all, it is clear that we have two seemingly independent links for the current and the voltage. There are just two independent processes going on. And these are orthogonal, that is, they are shifted 90 degrees. The voltage is transferred by the main flux, and you might say that the current is transferred by the lens hole or by equating the MMF. Now, MMF are not equal. There is a small drop to sustain the reactive part, and this is of course depending on the reluctance. That is, if the permeability of the material is very high, then this difference will become smaller and smaller. So this is just the amount of the magnetization current that you need in order to sustain the flux, which is a function of the voltage. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of